This is our second video for Chapter 14, Chemical Equilibrium. This series of videos starts off with how to manipulate K for different situations. So the first thing we're going to look at the relationship between K and chemical equations. When the reaction is written backwards, the equilibrium constant is inverted. For the reaction A plus B goes to C plus D, the equilibrium constant expression is for the K equals the products over the reactants where the coefficients become the exponents. If we write that reaction in the verse, for the reaction C plus D goes to A plus B, the equilibrium constant expression is K products over reactants. So the A, B over the C and D. So the relationship between these two K's is K forward versus K backwards. So you notice that these are just inverted. So the relationship is K backwards equals 1 over the K forward. If we change that direction that we write that reaction, we have to invert the K value associated with that reaction. When the coefficients of an equation are multiplied by a factor, the equilibrium constant is raised to that factor. For example, for the reaction A plus B goes to make C, the equilibrium constant expression is the products over the reactants. In this next reaction, we take that same equation and multiply everything by 2. So 2A and 2B's and 2C's. So the equilibrium constant expression is still products over reactants, but we have to take into account the 2 in the exponent. And if we factor this out, this would be the same thing as the K squared. So the relationship between the two different equations of the K new is going to be equal to the K original raised to the n power, where n represents the factor by which everything was multiplied by. So in this case, everything was multiplied by 2, so the K value would be K to the second power. So this is useful for equations if you look it up and maybe somebody has written the equation with like a half for a coefficient. So an example where this may be useful, let's say you wrote and balanced your chemical equation for hydrogen reacting with oxygen gas. So 2 equivalents of H2 with 1 equivalent of O2 goes to make water. But let's say when you look up the chemical equilibrium in a textbook, you're trying to find the K value, the author wrote the chemical equilibrium as H2 plus 1/2 O2 goes to make water. And so the textbook gives a value of some K equilibrium for that. Well, if you want the K equilibrium for the equation that you wrote, you're going to have to take that K equilibrium that you found in the textbook here and square it so that the equilibrium expression for those reactions are the same. When you add equations to get a new equation, the equilibrium constant of the new equation is the product of the equilibrium constants of the old equations. So for our example, we're going to be looking at two reactions where A is converted to B and then B gets converted to C. So our second reaction is B gets converted to C. So the equilibrium constant expressions are K1, this is for the first reaction, products over reactant, concentration of B over A. And the equilibrium constant for reaction 2 is still products over reactants, so concentration of C over B. But let's say we add those two equations together. So the sum of those equations, so A goes to B and B goes to C. If we add those up, A plus B goes to B plus C. So if we were to write the equilibrium expression for the sum of these reactions, it would be products over reactants, so B times C over A times B. But notice that we can cancel out the B, just like we can cancel out the B here to get the overall reaction. And that overall reaction is the same as this one here. So the equilibrium expression for the new reaction is products over a reactant. So when you add equations together, you multiply the equilibrium constants. So we added equations 1 and 2 to get the new reaction equation, but the equilibrium constants were multiplied to get the new K value for the overall reaction. Now we'd like to talk about equilibrium constants for reactions involving gases. The concentration of a gas in a mixture is proportional to its partial pressure. Remember, PV equals nRT. So if we're relating molarity and moles to the pressure, these are going to be proportional to each other. Therefore, the equilibrium constant can be expressed as the ratio of the partial pressures of the gases. So for the reaction A plus B goes to C plus D, there are two ways that we can write this equation. We can do what we've been doing before, where we have the Kc, where C represents the concentration, and remember the brackets mean molarity. Or we can write the Kp, so this is equilibrium constant where P represents pressure. So the Kp is still the products over the reactants, but instead of using the concentrations and molarities, we're going to use the partial pressures of the different gases. So the partial pressure of C, the partial pressure of D, the partial pressure of A, and the partial pressure of B. And we still use the coefficients to make the exponents. So the coefficient for D is still the exponent for D, and the same goes for all the other components of the reaction. In calculating the Kp, the equilibrium constant using the pressures, the partial pressures are always in atmospheres. So you have to be in atmospheres. The values of Kp and Kc are not necessarily the same. Sometimes they'll be the same, sometimes they won't. And this is due to a difference in the units. The only time that Kp will equal Kc is when the delta N equals 0. And this means the change in the number of moles. So if you have the same number of moles of products as you do the number of reactants, then the Kp will equal the Kc. So the relationship between the Kp and the Kc, the Kp value is going to be equal to the Kc times RT raised to the delta N, where R is the gas constant and T is the temperature, so that temperature in Kelvin, and delta N is the change in the number of moles. So delta N is the difference between the number of moles of reactants and moles of products. So I'd like to show you how we can derive the relationship between Kp and Kc. So here we have the expression of the molarity of A. So remember the bracket means molarity. And we have the moles of A in Na over the volume, where Na equals the moles of A and V equals the volume of the gas. Now we use the ideal gas law, so PV equals nRT, so we're looking at the pressure of A with respect to the moles of A. Here we've just solved for the PA, so we took the Na and RT and divided by the volume. So we've divided both sides by volume to get the PA value here. Once we've got that value, that Na over V, that's the molarity. So we take that molarity that we found up here and substitute that in there. Then we solve for the molarity of A by taking the PA and dividing both sides by the RT. So the R's cancel out, the T's cancel out. So the concentration of A is equal to the PA divided by the RT. So we're going to use that same expression. Here we've just replaced the A with the X just to represent a generic material. For the reaction A plus B goes to form C plus D, we have the equilibrium constant expression. So we've seen this several times where we have the products over the reactants. And we also, I'm showing the Kp value, so using the pressures of the gases. So again, products over reactants, where P is the partial pressure of component C. So using the Kc value, what what we're going to do is substitute in the molarities. So here we've got the molarity for C. We're going to use this, what we initially derived on the previous slide, and substitute in. So the pressure of C over RT raised to the C coefficient. And we do that for each of the products and each of the reactants. Once we have the equation in this form, we can factor out 1 over RT. And then once we factor out 1 over RT, we have to remember the exponents C and D. Since these values are multiplied by each other and you've got the exponents are added together here with the rules of exponents. Then we can combine these two to get 1 over RT raised to the C plus D minus the A plus B. And notice that for the PC times the PD over the PA over the PB, we substituted in the KP value. So that's where that came from. So then I'm going to rearrange this to solve for the KP. So KP equals the KC multiplied by the RT raised to the C plus D minus the A plus B. And then rather than having all of this written out, I'm just going to change this to delta N to represent the change in the number of moles. Now I'd like to move on to heterogeneous equilibria. Pure solids and pure liquids are materials whose concentration doesn't change during the course of a reaction. Its amount can change, but the amount of it in solution doesn't, because it isn't in solution. So you can't express a concentration of a pure substance, because a concentration by definition is you've got a mixture. So if it's pure, you can't have a concentration of it. It just doesn't make sense. So if you have something that's pure, like a pure solid or pure liquid, it will not show up in your equilibrium constant expression, that mass action equation. So let me restate that again. Because their concentration doesn't change, solids and liquids are not included in the equilibrium constant expression. For example, for the reaction A plus B goes to C plus D, notice we've got the states here. This L means liquid, and if it's in the liquid form, it's got to be pure. And if it's in the solid, if you got the S here, this means it's in the solid form. If it's in solid form, it also has to be pure. Now the aqueous means that it's dissolved in water. So if it's dissolved in water, you know it's going to be a mixture. And you can express that as a concentration. So if we write the equilibrium expression for this, it's still products over reactant. But because this is a liquid and this is pure, we're not going to see it in the equilibrium constant expression. And because the A is solid, it's pure, it's also not going to show up in the equilibrium constant expression. So we're still going to have the products over the reactants. And remember, don't forget to raise the concentration to the exponent relating to the coefficient in the balanced chemical equation. So now I'd like to show you an example of a heterogeneous equilibrium. Here we're looking at the reaction of two carbon monoxide molecules in the gaseous form will then go to make CO2 gas and carbon solid. So we've got the same thing in both bells, but bell jars. And both of these are closed systems. So notice you've got the lid on the top to keep the gases from escaping on both sides. And in both jars, I've got some carbon solid sitting at the bottom. In the first jar, I've got some carbon solid, and in the second jar, I've got even more carbon solid. Now the carbon solid, this is a pure substance. It's not going to interfere or change the equilibrium if I change the amount of carbon solid. This is because it's a pure substance. But we actually have a mixture in the gas phase. So let me count up the number of CO2. So there's 1 CO2, 2, 3, 4. So we've got 4 CO2 and 1, 2, 3, 4 COs. And I've got 1, 2, 3, 4 CO2s on the right hand side and 4 COs as well on the right side. So notice that changing the amount of carbon solid did not change any of the reactants. or the product concentrations due to the CO gas and the CO2 gas. So it did not affect the equilibrium concentrations. The amount of carbon is different, but the amounts of CO and CO2 remain the same. Therefore, the amount of carbon has no effect on the position of the equilibrium. So remember that equilibrium constant expression would be products over reactants, so the CO2 over the CO concentration raised to the second power. And again, we do not show the carbon in that mass action equation because it is a solid and it is pure. And we can also express that Kp value, so the pressure equilibrium constant, as the partial pressure of the CO2 over the partial pressure of the CO squared. Here's a little quick quiz question for you. Are the Kc and Kp values going to be the same? If you answer no, you'd be correct, because you have 1 mole of gas on the product side and you have 2 moles of gas on the reactant side. So the Kc and Kp values would be different. Now let's talk about calculating the equilibrium constants from measured equilibrium concentrations. The most direct way of finding the equilibrium constant is to measure the amounts of reactants and products in a mixture at equilibrium. And actually you only need to measure one amount. Then you can use stoichiometry to calculate the other amounts. The equilibrium mixture may have different amounts of reactants and products, but the value of the equilibrium constant will always be the same. Now the equilibrium constant would be the same as long as the temperature is kept constant, because those equilibrium constant values are dependent upon the temperature at which they're measured. And the value of the equilibrium constant is independent of the initial amounts of reactants and products. So no matter how much you start of the reactants or the products, the equilibrium constant will always come out the same. So to illustrate this data, we have 4 different reactions with different starting materials of hydrogen gas, iodine gas to form 2 equivalents of hydrogen iodide gas at 445 degrees C. So in the first one we have only reactants. We have 0.5 molar H2 and 0.5 molar I2 and no product. And if we measure those values at equilibrium and we plug those into our equilibrium constant, we get an equilibrium constant of 50. So if we plug that into our mass action equation, our equilibrium constant turns out to be 50. Now if we start with no reactants and only product, we can measure the equilibrium concentration values, and this is what we found. Plug those into our mass action equation, and notice that the equilibrium constant also comes out to 50. Well, let's try this again. Let's start the reaction again, where here we started off with half a molar of each of our reactants and half a molar of our product. Well, once it finally reaches equilibrium, we measure those values. When we plug those values into our mass action equation, we still get a constant of 50. So no matter what we start with, when it finally reaches equilibrium, the ratio of the products to the reactants will always come out to the same equilibrium constant value. So calculating the equilibrium concentrations. Stoichiometry can be used to determine the equilibrium concentrations of all reactants and products if you know the initial concentrations and one equilibrium concentration. Let's suppose you have a reaction where 2A molecules combine with B to make 4 equivalents of C product, with initial concentrations of A at 1 molar, B 1 molar, and C you have none. You then measure the equilibrium concentration of C as 0.5 molar. Well, one of the first things we like to do is we like to set up our ice table, and you will be making lots and lots of ice tables, and this is very important to us. So our ice table is where we show the initial concentration. So that's what the I stands for, initial molarities. And then the C stands for the change in concentration, and the E stands for the equilibrium values or the end values. So when we set this up, A and B are our reactants and C is our product. So I'm just going to draw a line here just so I can make the difference between our products and our reactants. So I put in our initial values of 1 molar A, 1 molar B, and 0 amount of C. Now they also told us that we measured the equilibrium concentration of C as 0.5 molar. So at the end it was 0.5 molar. So if we went from 0 to 0.5, the change had to be positive 0.5. Now if we want to find out how much B was consumed to make C, we can use the coefficient. So there's 1 B for every 4 C. So 1 B molecule is consumed for every 4 C that's produced. So the change in B is going to be 1/4 the C change. And it has to be a negative because we're losing B, because we're making product and we're using up our reactant, so that's going to be a negative value. So if I wanted to find the change in the B concentration, I relate it to our C concentration using the chemical equilibrium expression, using the balanced chemical equation. So for every 1 B you use, you'll produce 4 C. So to find the change in B, it's 1/4 of the C change. And it's a negative value because we consume our reactant to make our product. So if you're consuming something, it's going to be a negative change. If you're producing something, if you're making, it's going to be a positive change. Now we can do the same thing for A. Notice that A has a 2 to 4 ratio. So the change in A, we're consuming A to make C, that's going to be 1/2. So minus 1/2. So rather than writing negative 2/4, we're going to reduce that down to minus 1/2 the change in C. So if we do the math there, we'll find out that the ending molarity of A is 0.75 and the ending molarity of B is 0.88, and we had already determined that the C value was 0.5. So this is how we calculate the equilibrium concentrations using the balanced chemical equation in stoichiometry. Now another thing that we will need to use when we talk about equilibrium are the reaction quotient. And the reaction quotient is an expression of the products of reactants, but it's not for an equilibrium. So if a reaction mixture containing both reactants and products is not at equilibrium, we need to be able to determine in which direction we'll proceed. Do we need to make more product or do we need to make more reactant? So to figure this out, we have to compare the current concentration ratios to the equilibrium constant. And the concentration ratio of the products raised to the power of their coefficients to the reactants, also raised to the power of their coefficients, is called the reaction quotient, and that's abbreviated Q. So using that generic equation again here, A plus B goes to C plus D. The reaction quotient is products over the reactant. And you can do the same thing if we want to use pressure to relate the concentrations. So using the reaction quotient to predict the direction of change. If Q is greater than K, the reaction will proceed fastest in the reverse direction. That means the K value is too large, you've got too much product, so you're going to have to go in the reverse direction to get back to the equilibrium value. So the products will decrease and the reactants will increase. If Q is smaller than K, the reaction will proceed fastest in the forward direction. The products will increase and the reactants will decrease. Now if you have a Q value equal to K, this means that you've reached the equilibrium. So the products and the reactants concentrations will not change because you're already at equilibrium. If a reaction mixture contains just reactants, the Q will equal 0. So Q is products over reactants. And if it just contains reactants and the products is 0, the Q has got to be 0. So it's got to move in the forward direction. So you've got to increase the numerator to get to the equilibrium. Let's look at the opposite of that. Let's say if the reaction mixture contains just products. Well, again, remember Q is products over reactants. And if you don't have any reactants there, you've got a 0 in the denominator. That's undefined, and the Q approaches infinity. So to fix this, to reach equilibrium, you've got to start producing some reactants. So the reaction will proceed in the reverse direction. Now sometimes the math associated with solving for these equations can get a little bit tricky, and there's some approximations that we can use to simplify the math. So when the equilibrium constant is very small, so something like 10 raised to the -8th or 20 or something like that, when it's very small, the position of the equilibrium favors the reactants. For relatively large initial concentrations of reactants, the reactant concentration will not change significantly when it reaches equilibrium. So let's say we're talking about an initial concentration and we lose some of that reactant, and it's a very small amount. If this is a very small amount, the initial concentration, that change at equilibrium, so the concentration at equilibrium will be approximately the same as the initial concentration. What you're saying here is this change in the initial concentration is so small, it's negligible. Think about if you have $1 million. So your $1 million is your initial concentration. If you lose a penny, you're not that worried about it. And if you were asked how much money you have, you'd probably say you're a millionaire, because the loss of that one penny is very small compared to the large amount of money that you have. So even though technically you're not a millionaire, it's close enough. And so that's where we'll use that approximation. That's where you're approximating the equilibrium concentration of reactant to be the same as the initial concentration. And we are assuming the reaction is proceeding in the forward direction. We can check our approximation afterwards by comparing the approximate value of x to the initial concentration. If the approximate value of x is less than 5% of the initial concentration, we can assume the approximation is valid. Again, if the approximate x divided by the initial concentration times 100 is less than 5%, we can say that we're good to go and that the approximation is valid. So that ends our video for part 2 of chapter 14. There's a third video that shows how to do some example calculations, and then there'll be a fourth video to finish out the chapter relating to Le Chatelier's principle.